As I introduced just before, I am a chemist and I am presenting today chemistry related research. It is actually solid state chemistry research where no liquid is used or no water is used. In general, chemistry research or more of the reaction research involves liquid, any kind of liquid, either organic liquid or water, but it does not include any water, just heat and then solid materials. So I'm talking about oxygen deficient perovskite, or generally we have heard of, I think, perovskite solar cells, solar panels. They are made up of perovskite materials, and we are trying to develop a catalyst of the material to split water molecules to generate hydrogen and oxygen. We know that hydrogen is used as fuel and oxygen is also used as fuel cell, oxide fuel cell, solid oxide fuel cell to generate electricity and heat. Now, in my lab, my students make a pellet like this one, and then if it is seen in the powder form, the color looks like this, and this is a powder filter. When we look our skin through microscope, the cellular structure looks like this. And similarly, onion is this, and then its cellular structure looks like this. So if we look this material as a molecular structure, like their cellular structure, the molecular structure of this material looks like this one. And this is actually perovskite structure, we can say. To understand this one, let us think about the ball and stick motor. Actually, this perovskite is the general formula in chemistry ABOC, where A is, if you know chemistry in periodic table, that is second group as a alkaline earth metal or calcium, strontium, barium, and B is iron and cobalt or manganese type transition metals. So this B cation is this one, a ball, blue ball at the center, and these red balls are this oxygen. And this type of structures, if many structures combine, we can see a scaffold-like structure here, a cubic cube we can see here. And in this cube, you will see this blue ball. A red ball connects to another red ball through this blue ball. So oxygen connects to oxygen through B cation, or oxygen connects to another oxygen through this B cation. Or similarly, we can see this blue ball or B cation connects to this B cation through this oxygen. So it is interconnected like that. And to understand this, or to make it easy to understand, we imagine, or imaginary planes are drawn connecting the oxygen atoms. So then we can see here octahedral structure or octahedral geometry. And corners of the octahedron are connected, occupied by oxygen, and then this blue ball is here inside this octahedron. And we can see here a octahedron making a cube, and inside the cube there is, at the center of the cube there is another sphere, big sphere, that is this A. So this is A, this is B, and these red balls are oxygens. And this cube forms a unit cell, a single unit cell of the structure. And many such unit cells combine to form a big material. This is perovskite structure. From these perovskite structures, we can remove some parts of these oxygens. And then we can see here this type of white patches. These are oxygen removed spaces, and we remove the oxygens in our lab like that one. And it makes the compound now oxygen deficient perovskite. When oxygen is deficient, now we can see two structures here. One, this is octahedral with oxygen, full oxygen, and when one oxygen is removed, now square pyramid is formed. So in this case, when there is oxygen and no oxygen, two oxygen oxidation states of this B cation are there. For example, if it is iron, then it may have +3, +4, or +2, +3 oxidation states. Different oxidation states will be here. So electron, now here charge transfer means electron transfer. In our wire here, electric conductivity, electrons are transferring. In the same way, here electrons transfer or charge transfer take place. When charge transfer take place, now oxygen, when oxygen combines here, then the oxidation state change, and then see here is no oxygen, again oxygen combine, then oxygen removes, again combine, removes, combine. So electron or charge transfer take place throughout the material. This is called polar mechanism in scientific or chemistry term. And here I am talking about the catalytic activity. So when it splits water, at that time also it functions the same way. When we keep it in water, the oxygen is removed, and then again oxygen is combined, again removed, again combined. Once go in, come back, go in, come back. In the material it happens, and it acts as catalyst like that to decompose water, H2O, hydrogen and oxygen. It breaks into by this mechanism. And in my lab, students prepare materials like this. The precursors compounds are generally oxides or carbonates. As I said, they are all solids, no liquid is used, and they are mixed uniformly in mortar, pestle, and this is not mortar, again, mortar and pestle, and then it is pelletized here with about 3-ton force or 1.5 megapascal pressure, and then this pellet is calcined at 1000 degrees centigrade for about 24 hours. Again, it is reground, and then the powder is again repelletized. Then it is sintered at 1250 degrees centigrade for 24 hours. Then we get this pellet, and we test the phase if it is pure material formed or not using X-ray diffractometer. Then we powder that material once the pure material, desired material is formed, and then we use this type of 3 electrode setup system. Here we can see this is working electrode, and it is catalyst material, and this electrode looks like this one. And this is plastic, this is carbon, this is glassy carbon, very shiny carbon, like it shines like mirror. And then we put this powder catalyst here, and then we use here a counter electrode, partner electrode, and this is reference electrode. It is silver chloride electrode. It looks like this one. The complete setup is here, and we connect the setup to this potentiostat. This is like a current and potential measurement device. Now, how do we know that the catalyst works better or not? It is represented like this one. If this here it is potential, this is potential in x-axis, and then current density or current in y-axis. Now, actually, in the beginning it shows the line parallel to this x-axis, and then it starts curving. The closer this curve starts to this side 0, the better is the catalyst, or it works better. Or sometimes it is also measured here at 10 milliampere cm square current density. If we draw a straight line, then again we get a straight line here on the x-axis. This is called overpotential here. If the overpotential is lower, now here it looks like around 1.55, and the lower the number, the better is the catalyst. And we published this paper in ACS Catalysis. In summary, before the summary, we did many materials. We tested as OER activity, for OER activity, and some of them worked better, some of them did not work. So what is my summary here is perovskite oxide can act as oxygen evolution reaction catalyst or water splitting purposes. And the OER activity of perovskite oxides can be improved by increasing electrical conductivity. When we measure the conductivity of the different materials, if the conductivity is better, catalytic activity is better. If conductivity is not poor, then catalytic activity is also poor. And then it can be improved by increasing structural order, means the vacancy, random or order. If vacancy is ordered, then catalytic activity is improved. And then we can improve it by adjusting the compositions. In just before we started, calcium, strontium, cobalt, iron, manganese. So cobalt, iron, manganese composition ratio, when we changed, then at certain point it gave better catalytic activity. That is why it is said adjusting composition. And the students who worked on these materials are this one, Snaya Sanchez, and then he is Tanner. This is Amira, the Shem guard, and this is X-ray machine, and this is Eliara, and this is Ebony. She was about to present today because of road condition. She could not come. And thank you, NSF, and then EBSCO, if any questions.
Yes, we do have time for questions.